All right, this is 7-1 in Advanced Algebra 2. Today talking about exponential growth, exponential decay. Exponential growth functions or decay, any exponential guy is in this generic form, y equals b to the x, where b stands for your base, b stands for your base, b stands for your base. An exponential growth problem, the base will be greater than 1 every single time. So you can see that in here it says here's the parent function of your exponential growth. It's f of x equals b to the x, but the base has got to be greater than 1. Can it be equal to 1? No. Then it wouldn't be exponential at all, because you can put 1 there, take it to any power you want to. 1 to the first is 1, 1 to the second is 1, 1 to the third is 1, 1 to the fourth is 1, 1 to the fifth. Wouldn't you just keep getting 1 back every single time if the base was 1? So check this guy out. Is he an exponential growth function? Yes or no? It's just like Megan says, it's all about that base. Is this an exponential growth? Yes or no? Well, what's the base? 2, right? You can tell it's an exponential equation because where is the variable located also? It's in an exponent. Cool. So this is an exponential function for 1. It is exponential growth because the base is more than 1. Rock and roll? Let's graph it. We will not use our graphing calculator. There is a non-calculator portion to this test. Again, these are fair game because this is real simple to make ourselves a table of values. Let's start with negative shui, negative 2, negative 1, 0, 1, 2, shui. And we may add some more on for our x values right there, but there's my basic starting points of x values that I choose. And here will be y's. Skip over the negatives, baby, and start right here. Here's your starting point. If x was 0, let's do a little substituting in. If x was 0, wouldn't you get this? 2 to the 0th power. Let me make that a little better. Sorry, 2 to the 0th power. Right? Isn't that what y would turn out to be? Well, what is 2 to the 0th power, baby? It's 1, right? So right here we have a 1. Awesome. I'm cool if you want to put this little stuff in here, since I'm trying to make you to do it without a calculator. If you want to jot yourself a little bit of sketching notes right here, little notes, it's like that's 2 to the 0th. It's really a 1. You can work your way down. You can probably do the rest of these without sketching stuff down, but if you put a 1 in for x, what's 2 to the first? 2. 2 to the second? 4. 2 to the third? 8. All cool with those, right? Over here with the negative exponents, let's go and substitute in. Wouldn't this be 2 to the negative first power, right? And we know about negative exponents. What do the negative exponents really do? They start with an R? Reciprocate what, though? The base. So isn't this really 1/2 to the positive 1 power, right? The exponent is still a 1. All the negative part meant was reciprocate the base. And what's 1/2 to the first power turn out to be? It's 1/2. Awesome. Then what about this bad boy? If we put a negative 2, you get 2 to the negative 2, right? But you have to reciprocate the base again, correct? Wouldn't that give you a base of 1/2? It's got to be in parentheses. And now it's to the positive 2 power. What's that turn out to be? 1/4. And finally, go for negative 3. What'd you get? 1/8. Compare these 3 blue numbers to these 3 numbers right here. Compare them. What do you see? They're the reciprocals. But look how plain Jane this guy is, right? When it comes to like doing all that graph translation theorem stuff, you know, it doesn't have anything added to it. There's nothing added to x. The a value is 1. See, here's the real guy. It's y equals a times b to the x minus h plus k. Right? That's the real exponential parent generic guy. You see how there was nothing for k, there was nothing for h, and a was 1 in that situation, and we have a b value. So real simple there. It doesn't always work this way, where these numbers will be the reciprocals of those. It does if it's super plain Jane. You with me on that? Super plain Jane function. Let's graph this guy. Okay, before we fill out all of this stuff, let's graph him. Let's fill out our x table. What did we go by in our x column? We went by what? 1, so let's do that. We got to label our scale on these. I like to put them all. Awesome. And then I'd like to continue this table out a little further, right? Going 2, 4, 8, it just doesn't really get me where I want to go. Let's put one more in there and just see what happens. What if x was 4, since our x scale went up to 4 on this guy? What would we get if we put a 4 in for x? What's 2 to the 4th, baby? Yeah, we know those numbers better than anybody else, right? You get a 16. Cool. These are the y values. Isn't the highest number in there now a 16? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces available to get up to 16. Going by 1s isn't going to make it. What would you like to go by? Let's go by 2s. So label that, all of them all the way up, 2, 4, 6, 8. Who do you appreciate? Oh, math teacher. That's hilarious. And then let's start plotting these. I'm going to save these blue ones for later. These nasty fractions, I start at 0, 1 is where I like to start at. Ooh, it's not even on my scale, but isn't it right there, right? Halfway between 0 and 2. Is everyone down with that? Don't let me go too fast. Then I want to go 1, 2, 2, 4, and 3, 8, and 4, 16. You see how that is most definitely not linear, right? They don't all line up. They are growing exponentially. Aren't they doubling every time? Isn't the growth factor like 2? Every time they doubled, it went 1, 2, 4, 8, 16. What would be the next one? 32, right? It just keeps doubling. Now let's graph all these little nuggets right here. If you went to -1, you have to get to 1/2. It's like, yeah, how am I going to get that? If you went to -2, you got to get to 1/4. Yeah! It's getting to the point where I can't even see these dots anymore. They basically fall off the map. But let's talk about it. What if we put a -4 in there? Wouldn't you get 1/16? Then if you put a -5 in there, wouldn't you get a 1/32nd, then a 1/64th, then a 1/128, and then etc.? What is happening here? They keep getting smaller and smaller and smaller and smaller and smaller and smaller and smaller, but what will they never reach? They will never reach 0 because that's an asymptote. You can keep taking half of something every single time, right? Don't you just take half of it and half of it and half of it and half of it? It will never ever happen. So we will connect the dots like so as best we can. But then we got to draw in an asymptote. And that's why I gave you a straight edge. Isn't our asymptote in this case at y equals 0? And what kind of asymptote is he? Horizontal, vertical, or oblique? That's a horizontal asymptote. So we want to label him HA. And where's he at? Y equals what? 0. This is your basic parent exponential growth. The base factor can change every single time in an exponential growth. As long as it's more than 1, this is basically your parent exponential growth right here. Because like I said, A was 1, there was no H value, there was no K value or anything like that. There's your parent guy. So what's the domain? Look from left to right. How far to the left would we go? -infinity. How far to the right would we go? All real numbers, dog. Is everyone cool with the domain? The range is low to high. How low does this puppy go? 0 not included, right? That's as low as it will get. And how high does he go? To infinity. Did we have any asymptotes? You know, see how it's got the S in apostrophes after, or in parentheses after that? It's like, hey, is there any? If there's 1, maybe there's more than 1 also. Do we have any asymptotes? Yep. And you don't just need to put y equals 0. First you need to tell me what kind of asymptote it is. Horizontal or vertical? What was it? So please put HA colon at y equals 0. We had a horizontal asymptote at y equals 0. All good so far. Then these last two things, we talked about end behavior. It'll be a little bit of a refresher. The left end behavior. Wouldn't you agree that that's this guy right here? Isn't this the left end of this thing? So talk about x. Where are the x's going as we go to the left? Are they getting smaller or bigger? Where are the x's going? So we'll say as x approaches, where's x approaching if they keep getting smaller and smaller and smaller and smaller and smaller and smaller? -infinity. As x approaches -infinity, comma, f of x This is really your y values, right? Where is y getting closer to and closer to and closer to every time I go this way? Where's it getting closer to? Where's y getting closer to? 0. Isn't that number, aren't these numbers in our table getting closer and closer and closer to 0? As x gets smaller, doesn't the y values get closer and closer and closer and closer to 0? Correct? Now let's switch them around. The right-hand behavior, that's this brother. That would be as x approaches what? Infinity, right? Because aren't the x values getting bigger and bigger and bigger and bigger and bigger, right? As we go to the right, comma, f of x. Well, where's the graph going? Where's it approaching? Isn't it going all the way up to infinity? Doesn't the y values get higher and higher and higher and higher and higher? So f of x approaches infinity. Same starting every time. As x approaches negative infinity, that talks about the left end. The right end talks about as x goes to infinity. Just tell me what the y values are doing, is what that last part is. F of x approaches meow or meow. Cool with exponential growth. Why was it exponential growth and not exponential decay? Just like Megan says. You know, Megan Trainor. It's all about that base. And tell me, the base was what? More than 1. Cool? So in exponential decay, here's the rules for the base. Exponential decay, same idea. It's y equals b to the x, but the base has to be bigger than 0 and less than 1. It's got to be between 0 and 1. It can't be 0, it can't be negative, it can't be 1. It's got to be between 0 and 1. So do you see the base right here? Isn't that between 0 and 1? That means he's an exponential decay. Cool? Let's set up a table of values. Same idea. Maybe we'll add more, maybe we won't add more. Those are your basics right there. Here's where I like you to start. Ba-boom! This is the magic starting point. If x was 0, we put a 0 in right here. What's 1/2 to the 0th power turn out to be? 1. Time out. In your parent function, what would happen if it was a parent function to where this is 1, this isn't there, and you put 0 in for x every time? What will the y value always turn out to be? This point is a very standard point in your exponential growth or exponential decay. It's the magic point, 0, 1. It's always happening in the parent function. If they do some translations to it, it changes. If they do some dilations to it, it changes. But this is the magical parent point in that exponential situation. So what if x was 1? What would you get, baby? 1/2. Isn't 1/2 to the first power 1/2? Finish. What's 1/2 squared? 1/4. With a pen, maybe. Come on, dude, work. 1/4. 1/2 cubed is 1/9. And then isn't this Mr. Plain Jane? So how will these numbers relate to those numbers every time? They'll be the reciprocals. What did I do? 1A. Thanks. I don't know what I was doing. How will these numbers relate to these every time? They'll be the reciprocals. Let me show you. Because if you put 1/2 to the negative first in there, what does the negative exponent mean you're supposed to do? Reciprocate the base. And wouldn't you get 2 to the first power, which would be 2. So 2, 4, 8. Cool. Let's go one further this way. Let's put a negative 4 in there. What would you get if you put a negative 4 in there? 16, baby. Awesome. Scale me up. Scale. X's went by 1s. What do you want to go by on the y scale? 2, so that way we can get up to that 16. Oh. Don't say 16. Try to write 10 because you'll write 16. It's very bad. And plot those points. These over here are easier to plot, right? Stay away from the fractional points at first, right? Plot the big number points. So at negative 4, 16, that's way up yonder. Negative 8. Negative 2, 4. Negative 1, 2, 0, 1. And then little guy. They basically don't matter after a couple of them. You know, they're just getting closer and closer and closer to the x-axis. Connect together, drawing your asymptote. Please don't try to cross the x-axis. Asymptotes are always dashed lines. Meow, meow. Label him. Ha! Because he's a horizontal asymptote. That's redonkulous. Before we fill out this stuff, let's look at these two if I clean this up just a little bit. This is exponential decay. Look at it. What's happening as you look from left to right? Where's the curve going? Up or down? Doesn't it go down, right? It's decaying. Exponential growth, doesn't it increase as you look from left to right? Right, so let's fill this out. What's our domain? From left to right. Isn't all real numbers still possible? Doesn't it go from negative infinity to positive infinity? Yay! Range, low to high. How low does she go? 0 non-inclusive again, all the way up to infinity. We have an asymptote. What kind of asymptote is it? Horizontal asymptote at y equals 0. Left end behavior. As x approaches where? Where are we going when we go left? Negative infinity. F of x, where's the graph going? As I go to the left, where am I going? Up. How high will I go? To positive infinity. Cool. How about the right end behavior? As x approaches infinity, right, because we go to the right, where does the y values go? It approaches 0. An arrow. Cool. Pretty basics right there. Parents, parents, parents. Because the number in front of the base was a 1. They didn't add or subtract anything to your exponent. They didn't add or subtract anything here. Let's do some translations on these bad boys now. Purple note card. What a great note card it is. The purple note card. So we'll do all this stuff. It's basically telling us to go through the purple note card. The purple note card has 4 steps. Again, we could care less about steps 3 and 4. We just really care about steps 1 and 2. 1 is if it gets reflected over the x-axis. It's a little trickier this time because the a value is a number in front of the base, right? We got to watch out for that base in this situation. The base is what the exponent's raised to, okay? The number in front of it is the a value. So if that's less than 0, if it's negative, you know, you get reflected over the x-axis. Translations. Folks, I think we're trying to prep you how to type this in your calculator also. You should end up putting parentheses in this problem. We'll do that as we go. But the translation is, again, h. You see how it's the opposite of this guy, k. And didn't we realize on the front page that either exponential growth or exponential decays have horizontal asymptotes, correct? They have horizontal asymptotes only. There are no vertical asymptotes, so the horizontal asymptote will be at y equals wherever that k value is, where it got translated to. Okay, that k value moves it up or down, correct? So that's where the horizontal asymptote goes. It either goes up or down with the graph. Rock on? Then there's a whole lot of more things that we need to do. We'll just take them one at a time. First thing it says, figure out if this is exponential growth or exponential decay, and circle it. How do you know? What are you looking for? The base. What is the base in this problem? 2, so that would be an exponential growth. Cool, because its base is bigger than 1. Now, part B is let's do the graph translation theorem. I feel it is totally necessary for you to do this. Just in case you realize you wanted to type that in your calculator, which you don't need to do these problems. If you was to want to type 2 to the x plus 3rd power, you've got to put that in parentheses. Cool? Did this guy get reflected over the x-axis? That's what the 1 and the 2 for, the 2 first steps on your purple note card. Did it? You're looking at the a value, which is right here. What is the a value in this problem? Is it 1 or is it 2? It's 1. It's the number in front of the base. There is no number in front of the base, so it's like that's 1 times all this stuff. If it's negative, it got reflected. Did it? No. Translation, Same concept. We'll put a capital T, and we'll realize this controls the x, right? If that's a plus 3, where are we going? Negative 3, comma, then we go down 5. All that's peachy keen, right? Nothing new there. Here's some new things, though. First, I think it's very, very advantageous for us to recognize where the horizontal asymptote is before we graph this. Where will the horizontal asymptote be at? Y equals what? That's still not that new. We just did that last chapter. But now it's about where the magic point goes. Remember the magic point? Here's the magic point. The point 0, 1 is the magic point. We're going to make a sketch of this graph, and the only point that we're going to accurately put is where 0, 1 translated to. So here's what we got to do. Let's start with 0, 1 right here. And you first need to know, that's why this is step 1, if it got reflected over the x-axis. Did it? No, it did not. What if it did? Where would it go? Here it is. There's 0, 1 right there. And if I reflect it over the x-axis, wouldn't it go right there? Doesn't it totally change it to the point 0, negative 1 instead? You with me on that? But did that happen on this problem? Yes or no? No. Didn't it move 3 units left and 5 units down, correct? And that's just simple addition. It's the old translation vector stuff you should have done last year in geometry, like to where you have a negative 3, negative 5, maybe. Take 0 and subtract 3 away from it. Where would you go to? Negative 3. If you were at 1 and you moved 5 down, where would you be at now? What's 1 minus 5? Negative 4, correct? Doesn't the point 0, 1 move to negative 3, negative 4? You with me on that? So watch me move it. Just don't do this. Just watch me. Isn't this 0, 1 the way it is right now? This says it's supposed to go 3 left, 1, 2, 3, and 5 down. 1, 2, 3, 4, 5. Boom! Isn't that at negative 3, negative 4 right there? 1, 2, 3, 4 below the x-axis, correct? You see how it was already 1 above the x-axis. We're not starting from the origin. We're starting from 0, 1. Cool? So let's pretend that you have this now. The first thing you graph is the horizontal asymptote. Graph it. The scale, we don't need, if we're not going to go by anything, since this is a sketch, we don't need to put a scale or anything on there. If you're going by ones, you don't have to. If you want to go by something else, you do have to change the scale. But my horizontal asymptote is at y equals negative 5, so 1, 2, 3, 4, 5. Awesome. Label him also, HA, y equals negative 5. We want to plot the new point of where 0, 1 translated to. That's this guy right now. Where is our new point located at? Negative 3, negative 4. So 1, 2, 3, 1, 2, 3, 4. It better not be on the asymptote. I can't touch the asymptote. And let's see. Let's see if it's on the correct side. What we should do on some of these, especially when we get little hairy, is realize, what should this graph look like normally? It was exponential growth, correct? What should it normally look like? The green one or the blue one? Which one is it normally? Isn't it the green one, correct? So it should look like this. Did it get reflected over the x-axis, though? Yes or no? No. So it should still look like this. You with me on that? The only thing is, it's just moved down and to the left. So shouldn't it just kind of do that? Isn't that what it should look like? You got to label this point, though, for me. I forgot to do that. Negative 3, negative 4. And that's what it should look like. Cool? Domain and range them. Give me the domain. Give me the range. I like to do this first before we do part C. We skipped over part C to do part D, E, and F, or whatever we got left. Domain, negative infinity to infinity, correct? How about the range? How low does it go? To negative 5, because it didn't 5 units down, all the way up to infinity. Cool? What's the last thing it asks us to do, really, in part C, is write that sentence. So what's the parent function of this guy? Let me erase all this nonsense that I have right here. What would be the parent function of this guy? Y equals, no b's, right? We got to put a number in for b. What's the parent function for this guy? 2 to the x. Whatever the base is, it will still be the base. That's the parent function, right? All this junk right here there was your translation stuff right there, the +3 and the -5 stuff, right? So what happened to this guy? The graph of y equals 2 to the x. Go ahead and start writing. The graph of y equals 2 to the x has been, the graph of y equals 2 to the x has been, then what do you want to say? Translated 3 units left and 5 units down. Let's go to the next problem. First, recognize exponential growth or exponential decay. Decay because the base is less than 1 and bigger than 0. Awesome, awesome, awesome. Note card. Number 1, did it get reflected over the x-axis? Yes, it did. Do you see the negative in front of the base right there? Cool. Translation, I'd really love it if you went up and put parentheses around that guy. It should be typed that way. Translation, where did he go? 4, 2. Right, 4 right, 2 down. All good? Horizontal asymptote, it will always have one. If it's exponential, there will always be a horizontal asymptote. Where is our horizontal asymptote at this time? Y equals 2. Right, whatever this k value is, boom, that's it. But now we've got a double tricky situation. Let's take the point 0, 1 and see what happened to it. And this is why the order of our purple note card really makes a difference. Because the first thing that happens to this is it gets reflected over the x-axis, correct? So if you were at 0, 1 and you reflect that over the x-axis, where does he move to? Yes, sir. We start. He gets reflected over the x-axis. Where does he go to? He goes to where? 0, -1. Cool. That's the first thing that happens is this dude boot, has to go here. Boot. Cool. Now he translates. Isn't that step 2? Now it's got to move 4 units right and 2 units up. Cool. So we have to do that to this guy. We have to move him 4 units right. Where would he go? Where would the x value turn out to be? 4. And then 2 units up, where would the y value turn out to be? At what? 1. Is everyone cool with that? Awesome. Now let's make a rough sketch over here. Exponential decay. Doesn't he normally look like this? Please put that rough sketch. Normally looks like that. The blue thing, right? That's an exponential decay normally. We've got all this info. Let's start our graphing because you don't have this yet. All right, let's start our graphing. First thing you want to graph is your asymptote. Graph the asymptote. And that's at y equals 2. All right, so I'm going to now. Ha. So we've done our asymptote. Now plot our new translation point of 4, 1. So that's at 1, 2, 3, 4, 1. What? What? That's below the asymptote. Aren't they normally above the asymptote? Right? But what happened to this thing? It got reflected over the x-axis, over the x-axis. So it normally is above it. Since it got reflected, it had to come down below it. Cool? The question is, what should this thing look like now? Should it look like this, or should it look like this? Right? What should it look like? Well, that's why we made this sketch. Can you see what that should look like if you reflect it over the x-axis? Shouldn't it look like that? Right? So which one's correct over here? The red one. Let me get out of here. The little sketch makes a lot of sense to do, and it should break a little faster than that, something like this. It's just a sketch, but we got to label this point at 4, 1. I keep forgetting to do that. My bad. Yes. So our domain is from negative infinity to infinity. Range. It does the old switcheroo on the range because doesn't the lowest that thing go is to negative infinity, correct? How come it switched around? Why did the range switch around? Because we reflected it over the x-axis. So now the lowest this thing goes is negative infinity, and the highest it'll get is all the way up to that asymptote of 2. Won't touch it. And then our sentence. The parent function is y equals 2/5 x, right? It's just take away all the junk. The base has to stay the same, and it'll be raised to the x power. So the graph of y equals 2/5 to the x has been reflected over the x-axis and translated 4 units right and 2 units up. Let's do it again. Just like anything, it takes practice, right? Is that exponential growth or exponential decay? First of all, can we realize why it's exponential? Where's the variable of x located at? Upstairs, right? Exponents. Cool. So it's exponential. Is it growth or decay? Remember, the base has to be either bigger than 1 or between 0 and 1, and this is the base. That negative has nothing to do with it. There's no such thing as a negative base. What is that negative doing to this thing? It's reflecting it over the x-axis. So is this exponential growth or exponential decay? Growth. Let's do this now. Let's make a rough sketch before we even get started. What does the parent look like? Will it go through the point 0, 1? Yes or no? There's your parent guy. It always goes through 0, 1, and its exponential growth, won't it go like this, maybe? My pen would work. Double whammy. Isn't that what he should look like normally, right? Purple note card him. Throw in parentheses around that guy because I like to. He should have got reflected over the x-axis because of him, right? And it translated where? 2 units right. Did it go up or down at all? No. All good with that? Ha! Horizontal asymptote. Located at y equals 0. How come the asymptote's in the same place as it normally is? Why is that asymptote in the normal position? It didn't go up or down at all, right? It didn't move up or down, asymptote still stays there. Where does the point 0, 1 move to, though? So, first question, do we need to do the double banger or just a one banger? Did it get reflected over the x-axis, yes or no? So he has to immediately change to this, correct? You must do step 1 before you do step 2. That's the whole concept of why we've been writing those out. Cool? This normal point moved here. Then it moved with this. It moved 2 units right and nothing up. So where would he go to? 2, negative 1. Cool? Asymptote, point. There's my asymptote, and I now need to go to the point 2, negative 1. Ah! Is that right? Quick check. Is that right? It's below the asymptote. Should that have happened? How come? It reflected over the x-axis, so everything whoop-hoo, flipped over. Cool? Here's this guy. Isn't that what he normally looks like? So sketch me the reflection over the x-axis of this guy, but make sure you go through that point. And you can even go to your basic sketch over here and see what it should look like first and sketch that. It should look like this, right? Shouldn't it look like that? And now just make sure you go through that point. Tricky, tricky, tricky. Domain, range. From a negative infinity to a positive infinity. Range, low to high. How low does that graph go? How high does it get? Get it written down for me. Low to high. One of those numbers in your range has to be your horizontal asymptote. It might be how high it gets, or it might be how low it gets. It just depends on if it got reflected over the x-axis or not. Sentence. The graph of, what's the parent function? Y equals what? 5 to the x, right? All the other stuff goes away. The negative goes away. The translation stuff goes away. It's just the base to x. And that's what she should read. Here's our sentence, like I said. Go ahead and try the next one on your own. Pause the video, give it a shot, and check when you're done with my answers. Here's what 6 should look like. Like I said, check it, and then go to the next one. We'll just keep doing one at a time. Pause the video, give them a shot. It's worth it. The whole reflecting over the x-axis thing. You didn't have to do that 0, -1 thing because this did not get reflected over the x-axis, so it's just one move. Okay, you just had to do the translation. So here's 7, right? It did get reflected over the x-axis, so that's why we had to move 0, 1 here first, then move it to 1, 1. If you're struggling with that, you just need to come see me. I'll help you with that. Don't forget to write your sentence also. Sentence, sentence, sentence. Just one more. Get that one done for me, please. And finally, this is number 8. Did not get reflected over the x-axis, so you don't have to do the cool to -1 sign. So on the back side, we got 2 basic formulas for exponential growth and exponential decay. Again, it's the same concept, guys. It's about that growth factor, about the base. This is the base right here. Whatever they're doing in there, A stands for the amount, like your original amount. In a banking period, you'll hear that called principal all the time. Your initial investment, like what was your principal, what was your initial starting value. That's this lowercase a. R is your rate that this is increasing by as a percent. So we wanted to change it to a decimal. And T is time in any kind of unit. They'll tell you if it's in years or months or whatever, right? T is time. Cool? And this is the amount over time, A of T, right? The amount as the time passed. So if the base is more than 1, shouldn't that be an exponential growth? Well, do you see how in this situation here they took 1 and added the rate that things are growing by? So wouldn't that base always be more than 1 in that situation? And how about this guy? Look at the base. What will the base be in this time? More than 1 or less than 1? It's always going to be less than 1. Same formula every time, except what the growth factor is right there. Sometimes it's bigger than 1, sometimes it's less than 1. Cool? So there's 2 different formulas, one for exponential growth and one for exponential decay. Where the heck does it say exponential decay at? I don't know. I might not have cut it out right, but it's there somewhere. Number 9, read it. You figure out by reading, is it a growth situation or a decay situation? This is a growth situation. It is amazing how that is so difficult for you in Algebra 1. Thank God you have matured mathematically, and you can read and see the word. It's going to grow by 3.5% annually, right? What does annually mean? Per year. From this much in 2006. Estimate team spending in 2016. Cool? First, let's write a generic formula for this guy, right? Your homework's going to ask you to do that. Please write a formula for the general case. Would you all agree? It's this one and not that one. Why? Because it's growth, not decay. Cool? I like to do this personally. I'm a fan of saying R equals, and I want to change that percent to a decimal. How many places do you move the decimal? 2 places to the left. What would that become? 0.035. That's 3.5%. Cool? So doesn't this need to go in there? aren't you going to add 1 to it right away? Right? So here it is. A sub t will equal, do you know the initial amount? Yes or no? 7.7 billion. We can keep it, or excuse me, 79.7 billion. You can keep it as 79.7 just as long as when you're done, what word do you need to put in your answer? Billion. You with me on that? So 79.7 times, watch this miracle, 1.035. Where did the 1.035 come from? 1 plus the rate, right? Now, as a percent, isn't that 103.5%? Isn't that number more than 1? And then I need to put it to the t factor, t power, where t stands for time. Since it was annually, we'll assume in years. So estimate team spending in the year 2016. The trick to that is you don't want to put 2016 in for t, because what year did this start? 06, and now we're in 2016. So how many years had passed in that situation? So please write this down. A of 10 equals 79.7 times 1.035 to the 10th power. Do you see where there was a t, we substituted 10 in for that situation? Cool. Now we can punch this straight in our calculator because we all have a graphing calculator. It will do the order of operations for you. So 79.7 parenthesis 1.035, close it up to the 10th. You see how all I did was type exactly what was written. Don't use multiplication signs if you don't write multiplication signs. Didn't we use parentheses instead? It's just that simple. Type what you wrote. And should it be more than 79.7 or less than 79.7? Since it was a growth, it better be more than what we started with. Boom. Cool. Let's round that to the nearest tenth, if we will. And then we'll say 112.4. A of 10 is about, is it 112.4? Anything else? Billion what? And then where does the dollar sign go? That's a big pet peeve of mine. It goes in front of the number, not after the number. That one makes sense? Growth. Growth. What is this base? More than 1. Rock on. Next guy. Find the magic word. Is it growth or decay? Growth or decay? Growth or decay? But what's the magic word? Eliminate, which means go down, right? So this is decay. See the rate? I'll put it off to the side, but I want it as a decimal. What does r equal as a decimal? Is it 0.0125 or 0.125? Move it 2 places. It's 0.125. Awesome. Now, if you need to use a calculator for this next part, do it for the next part, but don't we want this formula? Tell me about this base when we put it in there. Will it be more than 1 or less than 1? Because we're not keeping all of it, we're losing some. So if we want to take 1 minus 0.125 and figure that out, I don't care if you punch that in or not, but check it out. You're losing 12.5% of your caffeine. Doesn't it keep 87.5% of the caffeine in your system? Because 12.5% is being lost, 87.5% is being kept. So generic formula first, A of t equals, what's our starting amount? 35 milligrams, right? Times 0.875 to the t, right? Isn't that base less than 1 because it was a decay factor, right? So punch her in. And 4 hours, so A of 4 equals 35 times 0.875 to the 4th. I know it's a lot of writing, but the calculator does all the work. You can write 2 lines down and let the calculator do all the work. Where's my pause button? It's under here. So you should have got about 20.5. Label? Hours or milligrams? Milligrams. How's that abbreviated? Is it mg? I don't know. If I don't know, I'm going to write it out. mg seems like salt to me. No? Isn't that MSG? My bad. That's what salt is MSG. Next. Set it up. So here's our formula, right? Since they ask about atmospheric pressure, that's why 14 goes here, because that's our starting atmospheric pressure. This formula will now tell us about atmospheric pressure. Put 10 in, and it is equal to 14 times 0.8 to the 10th. A to 10 is about, to the nearest tenth, 1.5 what? Pounds per square inch. Awesome. That should be enough. Talk about the decay factor. There's some questions that ask you that. It's interesting, you know. It's like either a growth factor or a decay factor. That's the number that you put in for the base. But I find it interesting. What's the decay factor? 0.8. It's like some people are like, isn't the decay factor like 20%? You know, it's like that's the rate that it decayed by. The decay factor is 0.8. Yes?